Today, we are diving deep, right into the heart of the atom itself. We're going to tell a story about balance, energy, and a constant quest for stability. And our guide on this wild journey, it's the process we call radioactive decay.
So, let's start with the big question. What actually makes an atom unstable in the first place? It's a great question, but before we can get there, we got to take one tiny step back and just quickly remember what makes an atom, well, an atom.
All right, to get why some atoms are just fundamentally unstable, we have to talk about what gives them their identity. And it really all comes down to the tiny particles packed into their core.
Okay, first up, a key piece of vocabulary, nuclide. The best way to think of a nuclide is like an atom's super-specific ID card. It doesn't just say carbon. It tells you the exact number of protons and neutrons, and even its energy level. This means you can have two atoms of the same element that are actually different nuclides. Wild, right?
And that brings us to two other really important terms, isotopes and isotones. Now here's a little trick I love for keeping them straight. Just look at the letters. Isotopes have the same number of protons, and isotones, you guessed it, they have the same number of neutrons. It's a super simple way to never mix them up again. And this leads us to what is, without a doubt, the most important rule of the atomic world. The number of protons defines everything. It's the one thing you can't change. You can add or subtract neutrons to get different isotopes of, say, carbon, and it's still carbon. But you change that proton count by even one, and boom, you have a totally different element. Which brings us to the really interesting part, the zone of stability. I want you to think of this as the ultimate Goldilocks zone for an atom's nucleus. Not too many neutrons, not too few. Everything has to be just right. You see, the real secret to a happy, stable nucleus is the ratio of neutrons to protons. For the small, light elements, a simple 1-to-1 ratio works perfectly. But as atoms get heavier and start cramming more and more positively charged protons together, they need extra neutrons to act as a kind of nuclear glue, holding the whole thing together. So when scientists plot out every known nuclide on a giant chart, this amazing pattern appears, what they call the line of stability. It's the sweet spot. But what happens if a nuclide isn't on that line? Well, it falls outside this zone of stability. It's got too much energy, its internal forces are all out of whack, and in a word, it becomes radioactive.
We can even get more specific. Think of it like a map of instability. If a nuclide finds itself in area A, it's got too few neutrons compared to its protons. If it's over in area B, it has way too many neutrons. And if it's way up at the top in area C, well, it's just too heavy, period. And each of these problems requires a very different solution.
So how on earth do these unstable atoms fix their problem? How do they find a path to a calmer, more stable state? For every single one of them, the answer is the same: radioactive decay.
And radioactivity isn't just some vague, spooky concept. It's a process we can actually measure. It's the rate of decay, literally the number of atomic nuclei that are transforming every single second. And we measure this rate in a unit called the becquerel.
And the definition is beautifully simple. 1 becquerel, or BQ, means exactly one nucleus is transforming or decaying every single second. That's it. It gives us a really precise way to talk about just how active a radioactive sample is.
So how does this transformation happen? Well, to get back to that comfortable line of stability, a nuclide has to get rid of its excess energy. It's like it's throwing off a heavy backpack. And that energy it throws off, that is what we call radiation. The atom is literally ejecting energy and particles to find a more relaxed state.
Okay, so what does this whole process actually look like? Well, an unstable atom has a few different tools it can use to get stable. You can think of it like a toolkit. Let's take a look at the three main types of decay.
This table gives us a fantastic bird's eye view. Remember those zones of instability we just talked about? Well, for each problem, there's a preferred tool. Those super heavy atoms in Zone C, they love to use alpha decay. The ones with too many neutrons in Zone B use beta minus decay. And the ones with too few in Zone A, they use a process called beta plus decay. We're going to focus on the first two, since they're the most common. Let's start with the heavyweights. Alpha decay is the solution for those massive nuclides up in Zone C. The nucleus basically just says, nope, I'm way too big, and it spits out a bundle of 2 protons and 2 neutrons, which is actually a helium nucleus. And get this, because it lost protons, the atom literally transforms into a completely different lighter element. Mind-blowing. Okay, but what about the atoms that aren't too heavy? They just have too many neutrons? For them, the solution is this really clever bit of internal alchemy called beta-decay. You can think of it as a neutron conversion machine.
So how does this work? It's absolutely fascinating. Deep inside the nucleus, a neutron just changes. It transforms into a proton, which stays right where it is. But in that process, it kicks out a super high-energy electron, which we call a beta particle. And just like that, the atom has fixed its ratio. It has one less neutron and one more proton, moving it much closer to that stable line.
Now, here's a simplified way to help you visualize what's going on. Just imagine that a neutral neutron is kind of like a positive proton and a negative electron squished together. If you think about it that way, it suddenly makes a lot more sense that when the neutron breaks apart, it can split into those two components. It's a great mental model.
But hold on, there is one last piece to this puzzle. You see, after an atom goes through one of these big changes, like an alpha or a beta decay, it's often still a little jittery. It's got some leftover energy. This is where gamma decay comes in. It's like the atom's final sigh of relief.
So, unlike the other decays, gamma decay doesn't change the number of protons or neutrons at all. The atom's already fixed its particle problem, but it might still be in an excited, high-energy state. To finally settle down and reach its ground state, it releases that last little bit of extra energy as a super high-powered photon, a gamma ray. When you put it all together, alpha, beta, and gamma decay, you realize you're just watching a fundamental process unfold. It is truly nature's balancing act, bringing the atom's long journey to an end. And here's the most important thing to take away from all this. This process, which might sound like total chaos, is actually anything but. Radioactive decay is a predictable, fundamental journey. It is the universe's way of taking something unbalanced and unstable and guiding it, step by step, toward a state of low-energy, perfect stability.
And that leaves us with a final, really powerful thought. If this journey from instability to stability is so orderly, so predictable, what does that allow us to do? How can we harness that predictability for incredible things, like creating unbelievably detailed images from inside the human body? It's pretty amazing to think about.